without the preparation. Now, if you watch the video and still make a bad grade, I can't help you with that. No, I'm just joking. Just send me a note, email, and I'll reset your attempt.
Okay.
Matter of fact, who was that? I can just do it now. I mean, not now, but I'll write your name down.
Juanita Smith.
Okay. I'll reset it for you today. Because I'm going to send that video out after class.
Okay. Okay, thank you.
Yes.
For the homework assignments, are we doing all the questions or just the highlighted ones?
Just the ones that are highlighted.
Okay.
And then if we do any other questions, then that's just icing on the cake. Because like we did this one right here the Friday. We looked at that one, so it's just icing on the cake.
Okay, and also for the problems that are highlighted in the syllabus, those are just for practice.
Yes.
Okay,
cool. The ones highlighted in the syllabus are practice problems. Yes.
Okay, awesome.
All right, let's do something real quick, just as a quick exercise to make sure that you're not slacking. Let's look at paclitaxel, which is a anti-cancer drug. My wife actually, when she was in chemotherapy before she passed, she actually was taking this drug. That was like the first thing they gave her. It's a version of Taxol, which comes from the Pacific yew tree, but it takes 100 years for one of those trees to grow back. And the bark from that tree, you're only gonna get like a milligram of this from it. So somebody had to figure out how to make it. So a professor down at Florida State actually made it, patented the synthesis, sold it to Bayer, and now he sold it for like $2 million, and then he gets royalties every time they sell this to a cancer clinic. So there's a lot of money in chemistry if you do it right. But let's pick out the chiral centers. How many chiral centers do you see here?
Hold on.
Real quick. And how and
11.
11. Yeah. Let's see. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Who was that? Was that you again, Natalie?
Yeah.
You're trying to get all the lunch money. I ain't got no money today. No, that's good. That's right, though. That's 11 stereo centers. Why is this not a stereo center? It's just a quick exercise to.
Which one?
Why is that not a stereo center?
It has the same two substituents.
It's got those two methyl groups. And because of that, that's a problem, right? That means it's got to have 4 different substituents, and it only has 2 substituents that are different. Are we okay with that?
Yeah.
All right. I just want to make sure now, because that's the kind of stuff that you'll see on a test. I might ask you, pick out all the chiral centers. And then I know for a fact there's another question I'm going to ask about the number of stereoisomers. So if you got 11 stereo centers, how many stereoisomers are possible? 2 to the what?
20. Oh, wait. 2 to the 11.
2 to the 11?
Yes.
I'm not expecting you to know that off the top of your head, but.
That's a lot, yeah.
You get it though, right?
Yes.
You also understand that that number, the fact that number of stereoisomers are possible, and you only want to make this one, right? That means you got to know your stuff, and you got to have reactions in place to set all of these stereo centers when you're making this compound. That's why it was I think it took them 8 years to finish this synthesis. The professor at Florida State. I can never remember his name. I know his first name is Robert. I think it's Robert Hoffman or something like that. 8 years, because you only want this. Why? Because this is the one that binds to the receptor that kills the cancer cells. Right? Not any of the other 1 million compounds.
Wow.
Yeah, it's very specific, right?
How come the carbon with the double bond O that's also attached to the nitrogen on the far left, how come that's not us?
Right there?
Yes.
That's you again, Juanita?
Yes.
Tell me why. What's the criteria for chirality? What's the number one criteria? 4 different groups, right?
Yeah.
How many groups are attached to that carbon?
Oh, it's only 3.
3. So it can be chiral. And plus, if it's got 4 different groups, that by default is going to be sp3 hybridized, right? And this is sp2. Any sp2 carbon can't be chiral. All right, so that's a good little warm up. Let's go down here to, it asks to draw the enantiomer, but we're not gonna do that. But you could, right? If I ask you to draw the enantiomer of this, and I gave you a blank structure, well, I gave you the structure without the chiral centers and then one with it, what would you do to every chiral center in there?
Flip it.
Reverse it. That's exactly right. So this would be wedged, this would be dashed, so on and so forth, all the way through that molecule. Everywhere you see a wedge, you would make it a dash. And everywhere you see a dash, you make, make it a wedge. Yes?
Mm-hmm.
All right, let's go down here and look at some of these other examples. Come on, Russell, get it right. Get your mind and your life together. All right, let's look at these examples over here. I know it's not a highlighted problem, but we gotta warm up before we jump over there in the deep water. All right, so tell me if C, if that this carbon in C is a, come on, Russell. This carbon, is that a chiral center? Why or why not?
No.
No.
Why
It
not?
has the same constituents on both ends.
It's symmetrical, isn't it?
Mm-hmm.
So that's a problem, right? What about this carbon? Is that a chiral center?
No.
No. Is that?
It's sp2, isn't it?
Yeah.
Mm-hmm.
All right. Now, what about this carbon right here?
Yeah, that one's good.
Yeah.
It's a chiral center, isn't it? Now, let me use this example to talk about configuration, right? So every chiral center has a configuration. That's what gives it the shape, right? It's either going to be right-handed or left-handed. We talked about that already, R or S, right? I think that was in the first set of videos I sent out. So it's either going to be R or S. The way you determine whether it's R or S is you got to do two things. You got to prioritize. First thing you got to do is prioritize. And so priority is based on atomic number. It's based on, I'm abbreviating atomic number as Z, right? You remember that from GChem, yeah? All right, so priority is based on the atomic number. And so if we look at the atoms, we're going to compare the groups. Now, for this example, I want you to make sure you understand this. If you don't see a fourth atom, it's understood to be hydrogen. And notice where it's going. It's going back into the page because the bromine is coming out of the page. Yes or no?
I was actually just about to ask that. Okay.
Yeah, it's going back. So anytime you see a stereo center like this, it's the hydrogen is understood because it's a skeletal form for one, and the direction of the hydrogen is based on what the direction is of the group that's on the wedge. So if that because remember, every carbon is a tetrahedral, right? And so if the bromine is on a wedge, then by default, the hydrogen is going back into the page. Go ahead. Somebody get ready to ask a question. Is that okay?
Yeah.
Yes.
Yes.
Right. So now let's prioritize these things. So bromine, we know is going to be 1, right? Because the atomic number is 79.
Right.
Hydrogen is always 4. Right? It's always your lowest priority group. And so now you got a carbon right here and a carbon right here. Now you got to pick between the two. Remember the other day when we were looking at determining whether something was a chiral center, and I told you about moving to the next atom until you get to a point of difference?
Yes.
Yes.
That's what you got to do here, right? So for these two carbons right here, looking at this carbon, which is a CH3, right? And this carbon is a CH2, but
It's connected to.
it's also connected to another carbon on that side. Are you following that?
Right.
So that carbon on the left is going to be higher priority. So we're going to call that 2 and that 3.
Okay.
So
yes.
When I first started teaching at Tuskegee, I spent a lot of time on this section trying to get folks to see in 3D, and I promise you I would love to do that. But right now we got to keep pressing because we in a compressed time zone. So If H is going back already, I'm teaching you a shortcut because y'all like shortcuts, right?
Mm-hmm.
Okay, great. If H is already going back, right? It's already on a dash. All you have to do in a situation like this is count to 3. And if it's clockwise, it's R. If it's counterclockwise, it's S, right? So here's 1, here's 2. Sorry about that. Here's 1, 2, and 3. Is that clockwise or counterclockwise?
Counter.
Counter.
Counter. So what's the configuration at bromine?
Oh, yes.
Right? Are you following that?
Yes.
Since H is already back, that's one of your other parts of your method for determining configuration, right? You prioritize and then you rotate to get H away from it. I know you saw that in the video when we talked about the steering wheel conformation or steering wheel, yeah. So get the top 3 priority groups facing you. That's another part of determining configuration. But we're gonna do it a shortcut method here. So since H is already back, you just prioritize, count, and what you see is what you get. Is that clear?
So would this also be a Fisher projection?
No, this is not a Fisher projection. We're gonna do a couple of those in a minute.
Okay.
All right. Now let's do the opposite of that. What if bromine is coming back like this? What does that mean? Where is H?
It's on the wedge.
Wedge. That's right here. Isn't it? Follow?
Mm-hmm.
Yes.
That's for any carbon. Whatever is wedged, if it's drawn in a skeletal form like this, and it's drawn in 2D and it's flat, if whatever is wedged, by default, the other group is dashed. It doesn't matter what it is.
Mm-hmm.
All right, so bromine, if I put bromine on a dash, that means hydrogen is wedged. What's the configuration there?
That one would be an R.
It would be R. It's got to be R, right? But let's see how we can say that or determine that using some methods, some methodology. You know it's R because when you look at the top example was S. But if we say this is 1 and this is 2 and that's 3, which way are we counting in?
That's counter.
It's still counterclockwise, isn't it? But the fact that H is on a wedge, we're just going to reverse it. So instead of it being S, we're going to call it R because of how H is oriented. That's the shortcut. If H is on a wedge, then it's the opposite. If H is on a dash, it is what you see. Does that make sense?
Yeah.
Mm-hmm.
Because when you take this one right here and flip it around, so let me show you what I'm talking about. We took it and flipped it around. It would look like this. Wouldn't it? If I took that and I rotated it, the whole molecule around, it would look just like the mirror image of the other one, which it is.
Mm-hmm.
Okay. Is that the same type of thing that I had asked a question in the chat about 5.39 and like I was trying to figure out why it wasn't R and why it was S. Is like, was that the same type of situation with that problem?
Yeah, you have to flip.
Which question was it? Was it on this sheet?
Yeah, it's 5.39.
5. Okay, here we go. Boom. Which one is it?
A.
A? Yeah, let's do A. Because I think we got it. We warmed up now. The juice is flowing. So let's do A. A, it has 1 chiral center. Again, why can't this be chiral?
Double bond.
It's sp2. Don't waste your time trying to figure that out. Why can't this be chiral?
It's now 4. Well, it's now 4 groups.
It's a CH2, right? It's got two of the same groups. Yes?
Mm-hmm.
All right, now let's do this one. So now we got OH is 1. Is that right?
Mm-hmm.
And then you have 3 choices for 2. You got the ethyl group, the methyl group, and then this other carbon down here. All right. Which one of those do you think is going to be 2? And how do you know?
The carbon down.
This one? Right here?
Yeah.
I agree. Right? Because this carbon, so let's look at it. So remember, ethyl is CH2, CH3. Following?
Mhm.
And methyl is CH3. So when I'm comparing these, I'm looking at the first atom, carbon, carbon, and carbon. Between these two, the ethyl and this one, those are both going to be higher priority than the methyl group.
Mm-hmm.
Right? The
Right.
methyl is going to be, in this case, 4. Right? It's your lowest priority group.
Mhm.
Does that make sense?
Yeah.
All right. So now we got the OH is 1, and then between these two, this is carbon. It's a carbon here and a carbon here. But then when we go to the next atom, this carbon right here is connected to an oxygen. This
Mhm.
carbon here is connected to a hydrogen. Right?
Mhm.
Y'all following that?
Yes.
Yeah.
So this is going to be this. That makes this group down here 2. Is that right?